Hey, YouTube, how is it going? I hope all is well. Today, we're going to talk about this little guy right here. What is this little guy? This is a choke. Not the kind that you perform in the bedroom with your girlfriend or your wife, but a choke for electricity. I'm just kidding. But of course, let's move on to something a little bit more technical. So what we're looking at here is the explanation of what a choke does in an amplifier. In your guitar amp, it basically acts like a current reservoir, smoothing the power supply output and reducing ripple ripple voltage and current. It's a rough way of saying that it reduces ripple. That's really all you need to know, is that it reduces the ripple. And it does so by storing up the current flow through it, and then releasing that energy nicely and smoothly. And it just does it in a way that is a little bit more efficient than a resistor would be. Mr. Aiken, check out his site. He's got these white pages that are tech info pages or whatever, white papers, etc., that really kind of answer all the possible questions that you could possibly have about this stuff. Of course, he says here it's used in place of a series resistor because the choke allows for better filtering, which means less residual AC ripple on the power supply. The other advantage is that it has less DC resistance and because it has less DC resistance, that means you have less voltage drop, therefore less sag. So chokes do kind of a cool thing. And of course, the Valve Wizard. He has a section on here. You can check it out, obviously, at your will. But he kind of shows all the different methods for it. And you can see here what the differences are between an RC network, which we already talked about in the last episode, the reservoir cap, and a resistor capacitor is what they call it, and an LC circuit. Now, an L in this nomenclature here stands for inductor. So L is the term for inductance in electrical terms. So the L in this case is the choke. That is the inductor that we're using. You still need a capacitor, so the capacitor still exists in the circuit, and there are a couple different ways that you can orient this circuit, but in general, it works kind of the same. Basically, all you're doing is replacing this resistor with the choke. And in doing so, you end up with something like this. As you can see, it is more efficient at dropping off the high frequency content. Remember that we're creating a high cut filter with this circuit right here. So we're rolling off the highs, and then it has a corner frequency that is determined by the resistance and capacitance of that network. Or in the case of a choke and a capacitor, it's the inductance and capacitance of that circuit. And therefore, it creates a slightly lower knee, or even the same knee, but there is a downside. It does have a resonant peak. So a choke and a capacitor circuit or an LC circuit has ringing that occurs at the corner frequency. That is not a good thing, and that is why the goal is to get sub 10 hertz. Excuse me. You are very welcome, and this show is now official. Just tell the wife it was me. Anyway, sorry. So, as you can see, it's more effective at rolling it off. You need to get below 10 hertz. At the very, very minimum, you need to get below 10 hertz, and you can kind of see why, especially if you're going to go with an LC circuit. That's because if that ringing gets up into the audible range and anything in your amp can amplify that, it will amplify and oscillate to the point where it could cause your amp to go into actual meltdown. Objectively, you're trying to get as close to zero as possible, but anything 1 hertz and below is probably within the objective area of pretty dang good. It's just at some point you come to a point of diminishing returns when you try to get below 1 hertz in some cases. But you can kind of see how a choke will help get you there a little bit quicker, if you will. So, there are a couple different ways to employ a choke. So let's look at the two different ways, and we'll kind of explain that as well. So one of the other ways that you can employ a choke is the choke input rectifier method. So it uses a choke in series with the rectifier output first. It's first in line, and you can kind of see this thing here that they're showing, which is this here. So if this is the output from your rectifier, whether it's solid state or tube, it does not matter, and then you go directly into the choke, you still need a capacitor, and that's where you would put it, is right here, and then this is your load. This would be your first node right here. So this would be your A node. So number 3 is the first thing that you would start to power off of. This would be where what goes to your plates on your tubes, or the center tap of your output transformer, let's just say. So that's what this choke input rectifier method looks like. Now, there is a difference between the two, and let's just look at the two, and then we're going to go over the benefits of one versus the other. So method A is the most common. This is the one that you see the most. And I'm sorry, this is a fairly small image, but it's the best one I could find that has both orientations, if you will, in one picture. So the typical method that you have here is literally just replacing the resistor that would normally go there with the choke. This is your A node here. So this is what would normally go to your plates, and then this would be what goes to your screens here. And then everything else down the line would be your preamp section and whatnot. So that's what this normally is. This one down here is our choke input rectifier method that I was just talking about a moment ago that looks like this. Okay? As you can see, it looks the same. So this is your rectifier. Again, it does not matter if it's tube or solid state. You go into the choke, very, very first thing, and then your A node exists here. So what's the difference between these two? You notice that I said this is your A node in this orientation, and this is your A node in this orientation. In this orientation here, this is what's the most high current portion of the amp, right? This is going to the plates of your power tubes, which means they have the highest current draw in the amp, and it's at this point here. So the choke doesn't see it. It doesn't know that it exists. It only cares about the screen grids and the remainder of the power supply, right? So that would include the preamp tubes. Down here, this is your first node. This is your A node right here, which means this is where the plates of the tubes would connect to, or the center tap of your output transformer, if you will. In this instance, this choke right here is seeing all of the power draw from the HT rail in its entirety. That includes the tubes, or the power tubes, and everything else down the line. That means this guy here in this orientation needs to be much higher in its milliamp value in order to maintain and handle all of that current flow. Up here, it doesn't worry about the plates of the tubes, or of the power tubes. Therefore, it can be much smaller in its milliamp current rating to do the same job. Okay, so we've kind of seen how that works. We kind of have an understanding now, at least, of what the two different methods are. What is the major difference between these two? Well, we've talked about it in the other episode, but when you have a rectifier, you get a voltage that comes out of it, out of the secondaries, right? So let's say it's 320 volts at this point. We're going to jump over here now, and we're going to say it's 320 volts because that's what's here, right? So you get a power transformer. Its secondary says 320, 0, 320. And normally what you do is you take that 320 volts and you times it by 1.4. What is 320 divided by times 1.4? It's 448. I remembered that off the top of my head. I did some studying for this for you. Hold on while I take a sip. Anyway, so 320 times 1.4 is 448. I'm not exactly sure how they got 468, but that's what they measured. That is fine. Maybe they had 124 volts that day actually at the input, and whatever. So they had a little bit more. That's fine. Okay, cool. So what happens when you put this orientation in here? So let's again go back to our other thing here and imagine that this guy right here, where these capacitors are, is replaced by our choke. Okay? So we're going to take the choke, we're going to move it from this point down to this point. What happens to this number right here? Well, unfortunately, in this orientation here, you do not times your secondary output voltage by 1.4. You can only times it by 0.9. So you lose a little bit of voltage doing this method right here. So 320 times 0.9 works out to about 288 volts. So you go from 320 volts, down to 288. So you would have to size up your power transformer, in order to make up the voltage loss that you have from doing this orientation here. But there is a reason why you would want to use this orientation. For this one here, you're going to use it with a Class A single-ended output amplifier. So that would be like a Fender Champ or any kind of amp that only has one tube and is single-ended. That's where you would use this. Now, why would you want to use this here? In a single-ended amp, you do not have the benefit of CMR, or common mode rejection, which is to say that the natural elimination of noise that is injected commonly across different phases of electrical signal. All right? So all that means is that with this guy here, since it does such a great job at minimizing ripple, right? This thing does a better job at reducing ripple than a resistor in this orientation would. But with these three components here, this would do a better job than that resistor would. So it gets rid of more ripple, which means that you get less noise injected into the whole of your HT power, power rail, right? So that's why you would want to employ this, is if you really, really need to get all the noise out of the HT rail, like absolutely have to get all the noise out, you'd go with this. And the best place to employ this would be in a single-ended Class A amplifier. Up here, it does a really good job, but you're not as concerned about it in this very first node because the output transformer has the benefit of common mode rejection. We talked about this before. But with that common mode rejection, the noise that is injected at this point into the power section of the amp, or the power tube section of the amp, is not as critical because it will kind of annihilate, if you will. It'll cancel itself out naturally. So let's go back to this here. So this kind of just gives you an idea of generally where they go. And now we're going to start talking about the specs of your choke. There's a Henry value that you normally see associated to them and a milliamp value that is associated to them. And it's a two-way street with it. If you go up in one and maintain the same size, the size of the choke gets bigger. If you go down in one and maintain the same milliamp current rating of that choke, it will get smaller, right? So in this orientation here that you see this, you can get away with a much higher inductance or Henry rating. So let's say 10 or 20 Henrys, but you only have to manage the screens and the preamp tubes. Well, the preamp tubes only pull about 1 milliamp a piece, and there's 4 of them. Well, 3 of them in this case. So let's just round it up to 10 milliamps total. We'll say that there's 1, 2, 3, 4. There's 6. Let's just say it's 10 milliamps total for all the preamp tubes. And let's say the screens pull another 10 milliamps or something, right? So that's 20 milliamps. So you're going to probably go a little bit bigger than that. Let's say 50 milliamps. So you only need a 50 milliamp choke here in terms of current rating to manage at 20 Henrys for all the remainder of this amp. And what would that look like in size? Well, let's kind of get an idea. So this here is a 2.5 Henry at 300 milliamps DC. So this is a pretty sizable choke for its Henry count, right? Scoozy. So what I mean by that is that this is rated for 300 milliamps DC. I got this to work in my 30 watt amp that I showed you with this guy the other day. The objective behind this was to be able to put it in a spot where it powered the entire HT rail. I got it just in case. I probably am not going to use it, but as you can see, it's still pretty sizable. It's about the size of my 18 watt transformer. output transformer, that is. So this guy here is about the size of the palm of my hand, and it weighs about 2 pounds. It's pretty sizable. It's only 2.5 henries, but it handles quite a large amount of milliamp current, right? If I needed this thing to handle 500 milliamps of current, even at the same Henry rating, it would almost double in size. It literally grows in that respect. If I kept the same milliamp rating for this, so 300 milliamps, and I went to, let's say 5 henries, again, it would nearly double in size. Or if I went to, let's say 10 or 20 henries at 300 milliamps, we're talking about a transformer that would be literally the size of your power transformer. And you have to imagine where you're going to place this thing. So this choke has to go somewhere. Generally, it goes in between your power transformer and the drink of choice that is always within arm's reach. Today we've got Pacifico. I bet you love how I tied that one in, don't you? Anyway, so you do have to consider where this thing is going to fit. And if you go ham on it and get a large milliamp rating with a large Henry rating, that thing can get really big, really quick, to the degree where it's almost the size of your power transformer or close to the size of your drink within arm's reach output transformer. So this one is pretty sizable. Like I mentioned, it's about the same size as the output transformer that I use for my 18-watt amplifiers. So it's pretty sizable, if you will. This here is somewhat representative of the size of a normal power transformer that you would have. And as you can see, it takes up a little over a third. It's almost half the size. So it's not without incident. There is a cost to using these. This thing here weighs about 2 pounds, maybe a little over 2 pounds, but right about 2 pounds. And you can imagine as it gets bigger, 5 pounds, possibly 10 pounds, So you're adding that much more weight. So it does have a cost-benefit analysis that you need to place in it. A choke is not necessarily always needed, especially when you consider how much these things cost. They're not cheap. I believe this one here was about $70. That's a lot of money to replace a resistor. Let me tell you, it's a lot of money to just replace a resistor. Now, again, even at 2.5 henries, this thing is much more effective than the same resistor would be in that spot. But there is the added benefit for a choke in an amp. So let's go back to this guy over here. So let's say in this amp here, they're actually getting 468 volts. Doesn't matter, whatever it is. And you look up here and you'll notice it says 468 volts here. And on the other side, it says 467 volts. It only dropped 1 volt over that thing. A transformer a choke, has very, very little resistance, which means it doesn't drop voltage the same way a resistor would. Most chokes are sub, 100 ohm, or maybe they're about 100 ohm, but they're pretty low ohms rating at least. Whereas most resistors that you would see in this location here would be 500 ohm, upwards of 1K to sometimes even like 2.5K or something like that, or 2K7 or whatever it might be. So you can lose a lot of voltage when you use a high value resistor here, but you need that higher value resistor in order to get that low frequency cutoff that you're looking for, that we were talking about, right? That sub 1 hertz, right? You got to get all that work done at this location here. A choke in this location is going to do a much, much better job than a resistor would and not lose voltage. So let's say you put a 1K resistor in here. Well, with 468 volts here, you might only get 430 on the other side. I don't know what it might be exactly, but I would imagine you lose 20 or 30 volts at least, which means everything else over here is going to be 20 or 30 volts shy. So if you can afford to lose that voltage down the line, that's okay. You can use a resistor in that place. You just have to plan ahead. If you don't want to lose that voltage, and I talked about needing on my Atlas build, that other amp that I said I finished more completely, in that one I did opt to use a choke. That was the reason why, is the voltage that I had here, I wanted to maintain more over on the other half of it, or on the other side of it. So I went with the choke in this position here in order to do so. So because I'm running slightly lower voltage amplifiers purposefully, in my case, I wanted to run more voltage on this side of this first node right there. And in order to do that, I had to use a choke to maintain the voltage that I wanted to have later on. So there are trade-offs. You do have to plan ahead. It's not just do it because you can. Another thing that you got to think about is, let's say you have an amp that normally has a resistor in this location. Simply throwing a choke in there can change the way that amp reacts and feels, and of course how everything else downstream of it works. If it's a high value resistor in this spot right here, let's say 1K or more, you're going to gain 20, 30 volts perhaps on the other side of that choke if you replace it. And that extra 20 or 30 volts can have an effect on the remainder of the amp that is good or bad. Not necessarily bad or good. It could be, again, user caveat emptor, right? It's up to the end user to kind of determine that value in it. So I hope that answers your questions about chokes. Probably more than you needed to know, but there's still obviously more about it. If you have any other kind of insights about them, please do leave your comments in the doobly-doo down below, or in the comment section or whatever. I'm not a super duper fan of chokes. I don't think they have quite the tonal impact that they say they do. I've used them in several different amps, and I can't say it makes the amp go from here to there. It's not a tonal increase. Where you do kind of get more benefit out of it is simply the working voltage that you have, so you can work the filtering a little bit different further down the line. You can either go lower in filtering or higher in filtering, and it doesn't, the effect is a little more noted that way, I guess you could say. Excuse. And then, of course, the weight, it's kind of a downside to have to fit this thing somewhere. It's got to fit somewhere. And then the added weight is kind of a bummer. And just the expense, they're not cheap. So, to literally replace a $2 resistor is kind of a hard pill to swallow when it takes a $70 part to do that. But the actual tonal aspect of the amp, I don't really notice that much. I think if you keep everything the same, so whatever voltage you had at the front end of the amp, you find a way to get that same voltage anyway, even using a choke, I think it's going to kind of sound the same tonally, but it might feel a little different with this. In theory, this should sag less. You should not have as much sag with this, which means it'll have a stiffer, more abrupt power supply, which means it should be able to just be more astute, if you will, more abrupt, right? Just more stern. That may be what you're looking for, and this may get you that if that's what you're looking for. I'm not going to say that it will, though. I had a PV6505, and I did replace the first dropping node resistor, the sag resistor as they called it, with a choke, and I didn't actually like it. I didn't like it at all. I kind of actually preferred it with the resistor in there. And you can actually run the resistor in parallel with the choke, which is to say that you put this over the top of the resistor more or less. So the resistor would just be here, right? And you just wire it around it, and it still does the thing. Because the resistor still resists current in a way, it still puts some work on this guy, and it does change the way it feel and sound a little bit. To me, I didn't really notice so much of a change in the sound as much as the feel. And the feel that I got from it, I didn't really care for with the choke. It's already a pretty stiff power supply anyway inside of a 6505, but I kind of preferred it without it. But since I spent the money, I kind of left it in there. I just put the resistor back in between. And without it, there was definitely a difference. And with it, it made up the difference that I liked. So I used both. That is a me thing. That is an experimentation that you can play with, though. So I hope this answers all your questions. And I just want to thank you for spending your time with me. So thank you so very much. We'll see you on the next one. Take care. Goodbye.